Circuit, I got 6 volts peak to peak on a 1 kilohertz on the function generator. So 1 kilohertz time force 1 millisecond. I got a 100 ohm resistor and a 1 microfarad cap. Now I need to find out first what Z total is for this circuit. In order to do Z total, I got to think back of Ohm's law. Remember Ohm's law? Okay. If that was a resistor, which it is, and this was a resistor, basically you just add them together and find current. Ohm's law still works, except for this is a little different. That's 100 ohms at an angle of 0 degrees. That, to figure out capacitive reactance, which is part of the impedance family. Capacitance reactance is 1 over 2 pi FC. When you do it on your calculator, it comes up to 159.2 ohms at an angle of 90 degrees, negative 90 degrees. Okay, so we've got negative there. You remember Eli the Iceman? Current before voltage in a capacitor. If we go set the voltage at 0 degrees, current would be 90 degrees ahead. And if you wanted Z, X sub C for the cap, you'd take this, put it up there, and divide the voltage and current, and you'd end up with an angle of negative 90, which gives you the impedance of it. That's why we keep coming up with that at an angle of negative 90. So 159.2 ohms at an angle of negative 90. Does that make sense? Yeah? Okay. So this is how they figured out that was a negative angle. Okay. Is by doing voltage over current, which in a cap, current's ahead. And when you take that, put it up there, you end up with a negative angle. So in order to find Z total here, I'm just going to add this and that up. So I got 100 ohms at an angle of 0 degrees, which basically is just 100 ohms, plus 159.2 ohms at an angle of minus 90 degrees. Okay, that was our minus 90 here that you already calculated out. So this one will plug into the calculator with the brackets and all, and it comes up with not 259 ohms, but 187 ohms, 187.96 ohms at an angle of minus 57.858 degrees. Now, if you're sitting there with your calculator, you probably think, well, we should stop and let me figure these out before you just throw the answers out at me. You didn't show up for lab. So we went through these in the lab on actually Wednesday and Thursday. So I got 187.96 ohms at minus 57.858 degrees. Now that is impedance total. If you're looking at the family of impedances, so Z total, you'd have X sub C as part of the family, X sub L is part of the family, and R is part of the family. So I've got resistance, inductive reactance, and capacitive reactance are all part of the impedance family. Okay. Now I know Jim wrote it ZC with a overbar on it, which great. I'm sure he explained what the overbar was, but okay. And ZL with the overbar and basically just R. That's all part of the impedance family. Okay. So Z total, 100 ohms minus J159.2. Now that's an interesting way to do it. I can do this in polar and I can do this in rectangular. Either way, that's 100 ohms minus J159.2. If you convert that to rectangular, guess what you get? Exactly the same answer. So there's some tricks you can do to get around having to do it all in polar. It's just that we like the answers written in polar because what does that actually mean sometimes? Okay, so now that I've got Z total in the circuit of 187.96 ohms at that angle of minus 57.858 degrees. Can I find total circuit current? Okay, total circuit current. I total is, for a resistive circuit, would be E over R to get I. So that's E over R. In this case, E is 6 volts peak to peak, and the total impedance is 187.96 ohms at an angle of minus 57.858 degrees. Gives us 31.92 milliamps, but you notice it has a phase angle to it. Okay, that tells me that it is not in the same phase as the voltage applied to the circuit, the 6 volts peak to peak. Now, I have to hang my head in shame over doing this, but you notice I put 31.92 milliamps peak to peak. We're going to relate this to the scope later, and everything's measured in peak to peak on the scope. So what I want to do is not have to convert this to RMS, which is what it's supposed to be in. So yes, I'm hanging my head in shame. Oh, woe is me. But I'm going to leave it in peak to peak for now, just to make Jim upset. How's that? Okay, so that should be in RMS, but it's not. So 31.92 milliamps peak to peak at an angle of plus 57.858 degrees. You notice that one was, Z total was at minus, and this one's at plus. Now that I've got circuit current, all the current in this circuit, you know, what enters the circuit is going to go back to the source. None of it falls off into the great ether. Okay, until you get into RF stuff where it gets, you know, 1 or 2 megahertz, it starts kind of running off into the air, but not here. So all the current that enters the circuit is going to head back to the source, or since it's AC, it's either way around. So voltage across the resistor. Do I have enough information to do voltage across the resistor? Think so? Okay. Voltage across the resistor would be current through it times the resistance. Just Ohm's law, right? Except for the numbers are these complex things. So the current through it is 31.92 milliamps peak to peak at an angle of plus 57.858 degrees times 100 ohms at 0 degrees, or just times 100 ohms. Okay. What I get is a voltage of 3.192 volts peak to peak. Okay, since we're still doing peak to peak. Yeah, and I'm still hanging my head in shame over that. Because it should be RMS, at plus 57.858 degrees. Okay, so now I have a voltage across this one. Could I get a voltage across VC as well? It's an IR drop, so current times the X sub C. This one probably should be X sub C. So I've got current through the circuit, 31.92 milliamps peak to peak at an angle of plus 57.858 degrees times, let's see, the impedance of the cap up here, X sub C, was 159.2 ohms at an angle of minus 90 degrees. Okay. I end up with a voltage across the cap of 5.081 volts peak to peak at an angle of minus 32.13 degrees. Wait a minute, where are you doing? That one and this one. It's kind of subtracted them too, didn't we? So we end up with 32.13 degrees. The voltage across the cap, and you notice that's negative, is different than the voltage across the resistor. Now, the voltage across the resistor is in phase with the current because the resistor has a 0 phase shift. So this 3.192 volts peak to peak is also in phase with the current in the circuit, which is here, it's in phase with it. Okay, so I have a voltage across the resistor, voltage across the cap, and these are the phases of those two. And if you wanted to figure out power, it's 3.1921912 volts peak to peak times the total circuit current. The resistor in this thing dissipates energy as heat. The capacitor does not. The capacitor stores energy and releases energy. Okay, so you charge it this way, then you charge it that way, charge it this way, and it's always charging, and that actually impedes current flow by the tune of 159.2 ohms at negative 90 degrees, as long as we're at 1 kilohertz. Okay, if we change this, that changes, and our angles also change. Total impedance of the circuit, everything changes. Okay, so what we're doing, we're making sure we do this at 1 kilohertz. Okay, what we need to find out, okay, power of the resistor is what is the dissipates heat. The energy is heat. So it's 3.1912 volts peak to peak at 57.588 degrees times 31.92 milliamps peak to peak at 57.85 degrees gives you 101 watts peak. Phase angle doesn't matter. Okay, it would be really nice to think that phase angle would, this negative phase angle would be refrigeration and a positive phase angle would not be. It'd be heat, but it doesn't work that way. Okay, so all we're interested in is 101, it's milliwatts. And you divide that by 2 because that's, you do an RMS value of watts. It's always an RMS. So we divide it by 2, divided by the square root of 2. We end up with 36 milliwatts of power being dissipated by the 100 ohm resistor. Okay. Next thing we're going to do is we are going to plot a phasor for the, this is all calculated. I'm going to put the voltage across the circuit here at 0 degrees, and I'm going to put the I'm going to plot the voltage across the resistor and the capacitor on this phasor diagram, and I'm going to plot it in peak to peak, which I know you're not supposed to do, but I'm going to do it anyway. When you answer questions on a test of mine, make sure you put them in RMS right under the peak to peak. Yeah, that would work too. Okay, so I got voltage on the resistor, across the resistor, came up to 3.192 volts at 57.858 degrees. So 57.858 degrees, it's a positive. Came 3.192 volts at an angle of 57.858 degrees. It was also the same plane as the current through that resistor, since there's no phase shift there, of 31.92 milliamps at an angle of 57.858 degrees. So I'm just going to plot that right here. If I was to do this on graph paper, I'd have all these all marked out as to, yeah, that's exactly 6 points or 6 volts peak to peak. And here is the voltage on the capacitor, which came up to 5.08 volts peak to peak at minus 32.13 degrees. So I'm going to plot that one down here at minus 32.13 degrees. and 5.18 volts. Something you want to notice is that the phase angle between current and voltage on the cap is 90 degrees here. If you add these two sets together, you should get 90 degrees. Okay, and 57.858 plus 32.13 is 90 degrees. Cool, huh? So, next thing we need to do is to try these out on the scope and see what this actually comes up to. Okay.